Welcome back, student, to our next lecture, Design and Analysis of Algorithm. Before going to the today's lecture, we will see what we have done in the last class. In the previous lecture, we have seen performance analysis of algorithm and space complexity, time complexity, and measures of time complexity. So these are the things we have seen. So now, how will you uh, find the space complexity and the time complexity with the help of mathematical notations? So that is today's topic is asymptotic notation, basic asymptotic efficiency classes. What are the classes are there, and which one is the best and which one is the worst? How will you identify? And three notations are there: asymptotic notation, which is very important to use to find the time complexity or space complexity, that is big O, big omega, and big theta. These three are the major uh, asymptotic notation for getting the time complexity and the space complexity. So in today's class we are going to see these all things one by one. So first we will see what is asymptotic notation. Asymptotic notation of an algorithm is a mathematical representation of its complexity. Is nothing but whatever the time is taking by an algorithm, with the help of mathematical representation we are assuming and we are getting the approximately value of that algorithm. In asymptotic notation, when we want to represent the complexity of an algorithm, we use only the most significant terms in the complexity of that algorithm and ignore least significant terms in the complexity of that algorithm. So in this, whenever you are uh, doing any mathematical representation of a time complexity or space complexity, for that it will take the most significant terms. Okay, it will take most significant terms, this one, and it will ignore the least significant terms in the mathematical representation, and this complexity is used for maybe for space complexity or time complexity. So the asymptotic notation can be used for the space complexity or time complexity. Based on this, we will get to know how much space is needed and how much time is taking. So these are the uh, things are there, and asymptotic notations we are going to take the big O and big omega and big theta. Okay. Before going to that, we will see the basic asymptotic efficiency classes. So this one is nothing but 1 to 10, 100,000, 10,000, that is constant. That is constant. After that number of steps, it will stop. So this is the best. If we have this is best. Okay. If you are getting the constant value, that means your algorithm is best. And next, log n, logarithm. Okay, and this is log n is little bit greater than constant. Okay, after log n it will be n. N is a linear, it is greater than log n, so it's going from best to worst. And next is n log n. n log n is greater than n log n and 1, means n log n is greater than linear, logarithmic and constant. N square is quadratic. N cube is cubic. N cube is greater than n2, n log n and 1. Then after that, like n cube and all the things, after that, if we are getting 2 power n, if we are getting 2 power n, this is called exponential. These are worst case. These all are the worst case. And n factorial, because here like 2 power n, if we are taking the example of n maybe 2, n is equals to 2, so it will be 4. Yes, but if the constant is 1000, example, okay, 10, if it is 10 or 100, so this is less than 2 power n only, but up to some extent the 4 is less, but when the increasing the number of n, then it will get suddenly up. In the graph it will go suddenly up. So because of that, this is exponential, and that is depend on the n value. If n value is 10,000, then this 2 power 10,000 will be more. And 10 the same way 10,000 factorial, then in this factorial also, that is taking like 1,999, like that will be huge number. So this is the worst case. If we are getting the answer after solving that, if you are getting this kind of answer like 2 to the power of n or n factorial, if you are getting the complexity this, then this is a worst case. If you are getting a constant value, that is a best. Okay, so this is the basic asymptotic efficiency classes, and some more are there. Like value of some important function of n is infinite. Like here n, what is n? Here n is a linear, log n is logarithm. Here log base 2 n we will read, or log n you can read. So log base 2 n and log n both are same, and n log n is getting this value, n square is getting 10 to the power of 2, n cube is getting 10 to the power of 3, 2 to the power of is 10 to the power of 3, n factorial is 3, 6, 10 to the power of 6. So these are the simple calculation for the given constant, logarithm, linear, n log n, quadratic, cubic, exponential and factorial. And the other name of this, the basic asymptotic efficiency classes, and the other name is growth. Order of growth. Okay, what is order of growth is also known as order of growth. In the exam, in the 2 marks, they are going to ask list the order of growth or define the order of growth. So you need to write this table, or you can write 1 less than log n, okay, less than n, less than n log n, less than n square, less than n cube, less than 2 to the power of n, less than n factorial. Like this you can write. Okay, next. And whatever we are performing here, this all the things, this we are getting the approximately value. What we are getting? We are getting approximately. As we have discussed in the previous videos, we will get the approximately value when we are going to write the algorithm for any problem. Okay, so now asymptotic order of growth, a way of comparing function that ignore constant factor and small input size. So as we have discussed, like three types of asymptotic notation we are going to see in your syllabus, and that is a big O, big omega, big theta. Okay, so here big O will represent as big O, and big omega will represent as this, and big theta is represented as this. So here big omega, big O, what is big O means? Class of function f of n that grows not faster than g of n, means it will work on a upper bound. So whenever we are solving any problem, at that time we will give the maximum time. Okay, and here class of function f of n that growth at least as fast as g of n, and here we are giving at least some of the equal or more than the expected time. Okay, and class of function f of n that growth at the same rate as g of n, means whatever the time you have given, accurate time will be there. So I will explain this with an example. uh, so here big O, we will see the big O. Here big O is used to define the upper bound of an algorithm in terms of time complexity. Means, what is this upper bound means? I will give the example. Like if you want to go from our college to Mehdipatnam, so we can reach from our college to Mehdipatnam in 25 minutes. Okay, exact time will be 25 minutes, but we are telling I will be reached there in 1 hour. So that means we are defining the upper bound. You should not cross more than 1 hour. So you have to be reach the your destination before 1 hour. So that is called upper bound. Like you have to give some maximum value, means maximum assumption we can say, or maximum time you have to take at last. So that this is a worst. Okay, so upper bound is nothing but we need to define the maximum time required. How much time you required, maximum time required, you need to specify. That means BigO notation always indicate the maximum time required by an algorithm for all input values. That means BigO notation describe the worst case of an algorithm of time complexity. So whenever we are getting the big O notation, so that is a worst case of algorithm, and every time it will take a maximum time. Okay, and let's consider this and we'll solve one example. Consider function f of n. Okay, f of n is function as a time complexity of an algorithm, and g of n is a most significant terms. Most significant terms means we are taking the upper bound and maximum time, so that is called upper bound. Here how will you represent this in a mathematical? F of n should be less than or equal to C is a constant, and g of n. For all n should not be 0, okay, and c should not be less than 0, that should be greater than 0, and n naught should be greater than or equal to 1. Then we can represent f of n as big O of g of n. Okay, big O of g of n. F of n is equals to big O of g of n. So this is a whatever the time complexity of f of n, that is equals to big O of g of n. So I will solve one example here, then you will easily understand here. Consider the following graph drawn in the value of f of n and g of g of n for input n value on x-axis, and the time required is y-axis. So here this line is a time and this is a input, and here n0. We are starting from here, and here you can see f of n is a right line and it is in the lower, means in the down, and g of n is on the top. Okay, so f of n, the time complexity, as we are telling the upper bound, so upper bound means it should go up, g of n should be go up the f of n. So we are giving the maximum time. So C g of n. In the above graph, after a particular input value n0, always C g of n is greater than f of n. Every time C g of n should be more than f of n. Then only we can say, which indicate the algorithm upper bound. Okay. So here we are taking one example for solving this problem, for checking is it a upper bound or not. So here I am taking one example. F of n is 3 of n plus 2, sorry, 3n plus 2. This is my time complexity of my algorithm, and g of n is equals to n. So here I will show you how we are taking this 3n plus 2. In the last class we solved the time complexity of our algorithm. I will go up and I will show you here. Like this we solved and we got the 4n plus 4. This is our time complexity of the algorithm. In the same way we are taking the time complexity here, 3n plus 2. And what is our g of n? G of n is n only. Whatever the n value you are going to take, that is a g of n. If you want to represent f of n as big O of g of n, then it must be satisfy, f of n should be less than or equal to c multiply g of n. For all value of c should be greater than 0 and n0 should be greater than or equal to 1. So here every time you should take n0 should be 1 only, then it will be easy for you to get the answer. You no need to take the maximum number. In n0, most of the time in the asymptotic notation, take 1 only, then it will be easy for you to solve the problem. So here f of n less than or equal to c g of n. So what is f of n here? F of n is 3n plus 2. What is f of n? 3n plus 2, that we have written here, and less than or equal to c constant. And what is g of n? Here we have a g of n is n. So this is our equation. In this, above condition is always true for all value of c is equals to 4 and n greater than or equal to 2. Example, if you have taken this number, these values here, okay, c is equals to 4 and n greater than should be greater than or equal to 2. So 3n here, 3n. So here that should be 3n plus 2 less than or equal to cn. So here in place of n and c we need to place these values. 3 into 2, that will be 6. 6 plus 2 is 8 here, and here less than or equal to c. What is c? 4. And what is n? N is 2. So 4 to the 4 to the 8. So 8 less than or equal to 8. So this is satisfying. Then it is a BigOhO of n. BigOhO of n. So this is a answer for the BigOhO of n. Next, big omega. Big omega notation is used to define the lower bound of an algorithm in terms of time complexity. That means we need to tell the minimum time, and it should be reached there before whatever the time we are giving, before that time only we need to reach there. Okay, so here that means big omega notation always indicate the minimum time required by an algorithm for all input values. That means big omega notation describe the best case of algorithm time complexity. Time complexity. So here whatever the time you are giving, that should be a minimum. That should be a minimum time. How much time is needed to solve the problem? At that time only you need to define. Okay, so consider function f of n in the time complexity of an algorithm, and g of n is the most significant terms. If f of n greater than or equal to c multiply g of n for all n greater than or equal to n0, c greater than 0, and n0 greater than 1. So as I told you, every time you have to take one only, then it will be good for you to solve the problem. Then we can represent f of n as omega g of n. So here in the graph, we will see the graph, then you will easily understand. In the difference between the big omega and big O is g of n is in lower bound, in the lower case, okay, lower bound, whatever the f of n, so whatever the time complexity of our algorithm, if it is completing before that, then this is a best case. Okay, what is our time complexity? Our time complexity is f of n, and this we are solving the problem before we are reaching to the f of n. So this is c g of n. Okay, so after multiplying with the constant value also, we must answer must be less than f of n. So what we can say, in the above graph for a particular input value n0, always c cross is c multiply g of n is lesser than f of n. Every time it should be lesser than g of n. What is g of n? G of n is a most significant terms which indicate the algorithm lower bound. So here also let's take the same example. F of n is 3n plus 2 and g of n is equals to n. If we want to represent f of n as omega g of n, then it must satisfy f of n greater than or equal to c g of n for all value of c greater than 0 and n 0 greater than or equal to 1. So in the same way, c of n plus 2 less than or equal to c n. Sorry, here the mistake is there. It should be greater than. Okay, it should be whatever the value is here, that should be greater than this value. So here if we are taking c of 1 and n greater than or equal to 1, so if we include n as a 1, so 3 ones are 3 plus 2 is 5, and what is c? 1, and what is n? 1. 1 ones are 1. So 5 here, it should not be less than, it should be greater than. So 5 greater than 1, the condition is true. So at that time we will say greater than f of n is 3n plus 2 and c of g of n is capital C of n. So here 3n plus 2 is equals to omega n. Okay, this is big omega n. So this is an example of big omega. Same time complexity problem based on your requirement, like what is the n value. Based on that, your program will define is it a best case or average case or worst case. Okay. The next one is big theta. Next one is big theta. So Big-Theta notation is used to define the average bound. So whatever the time we are getting, that should be average bound. It should not be in the upper bound or it should not be in the lower bound. It should be in average. So what is this? We are going to see now. So that means theta notation always indicate the average time required by an algorithm for all input values. That means theta notation describe the average case of algorithm time complexity. Like let's take the consider function f of n, the time complexity of an algorithm, and g of n is the most significant terms. If c1 constant 1 multiply g of n, it should be less than or equal to f of n, and here it should be greater than, and f of n is greater than or equal to c constant 2 point g of n for all n greater than or equal to n0 comma c1 comma c2 greater than 0, then n not greater than or equal to 1, then we can represent as f of n is equals to theta of g of n. So let's see the graph, then you will easily understand. In the graph you can see average means the function, this red line is f of n, and c of n is less than f of n, and c2 is a greater than fn. Okay, in above graph, after a particular input value n0, always c1 g of n is less than f of n, and c2 g of n is greater than f of n. So here is less than f of n, and sorry, here less than only, less than c of c2 dot g of n. Okay, because here we are taking the c and f, c1 and f1 is a lesser than c2. Okay, this above equation is that only this one. C1 point g of n less than or equal to f of n, and f of n is less than or equal to c2 dot g of n. So in the graph itself you can easily identify, and this is a average case. Let's take the same example and we will get the value of theta. So f of n is equals to 3n plus 2, g of n is equals to n. If we want to represent f of n as theta g of n, then it must be satisfy c1 g of n less than or equal to f of n, and here it should be less than, okay, less than or equal to c2 g of n for all values of c1 and c2 should be greater than 0, and n0 greater than or equal to 1. Okay, fine. Next, here uh, so we will see the example of the Big-Theta. I will show here. Okay, here we have an equation. What is this? This is f of n. Okay, and here we need to solve this problem. So here, what is my c1? C1 is 1. 1 point means 1 into g of n. What is g of n? G of n is n. So what is n now? N is 1. Okay, g of what is n? N is 1, and that should be less than or equal to f of n. What is f of n? 3 into what is n? N is 1. So you can write like 1 plus 2, and that should be less than or equal to c2. What is our c2? 5. c2 is 5 dot 1. This value you should assume in such a way that you will be satisfy the theta notation. Okay, in the exam it will tell you 3n plus 2 is theta asymptotic notation. So at you have to give such value in this, you should reach the theta notation, because we have taken the example for 3 big omega, big O, omega and theta. Big O, big omega, big theta, we have taken the same example, but we are giving the value in such a way that our condition should satisfy. So what will be the answer for this? Here 1 ones are 1. Okay, 1 ones are 1 less than or equal to 3 ones are 3 plus 2 is 5, then less than or equal to 5. So is this condition is satisfying? Yes, 1 is less than 5 and 5 is less than or equal to 5. Yes, this condition is satisfying, and this is a theta notation. Okay, here the some mistake is there. Okay, because of this greater than and less than, no problem. So this is a correct one. c1 dot gn less than or equal to f of n and less than or equal to c2 dot g of n. So this is, we can say, f of means, we can say here 3n plus 2 equal to theta of theta of g of n, g of n. This is, we can say. Okay, so this is about what we have seen in the today's lecture is BigOhO. Okay, and in the BigOhO, our uh, time complexity should be in less than the most significant terms. Okay, most significant terms. It will work on upper bound, and big omega is time complexity should be less than minimum of most significant terms. Okay, and this should be work in a lower bound. And the last one is t of n, means time complexity should be in a average bound. So these three are there. This is three very important for your exam. And for the mathematical calculation, we will use the asymptotic notation and we will get the approximately value of the algorithm. So what we have seen today, first we saw the asymptotic notation. Three notations we have: big O notation, big omega, and big theta. And we saw the basic asymptotic efficiency classes like constant, logarithm, linear, quadratic, cube, exponential. Okay, that is also very important. Then we saw that these three: big O, big omega, and big theta. So this is the thing we saw in today's lecture. I hope you understand, and thank you very much. We'll see you in the next class.